How an automatic transmission actually works. Your engine can make all the horsepower in the world, but without the transmission, none of it is getting to the tires. An automatic transmission has to take power from the engine, multiply torque when you take off, change gear ratios while you're driving, let the engine keep running while the vehicle is stopped, and send all that power to the drive shaft. And it does all of that with fluid, clutches, gears, and hydraulic pressure. So how does an automatic transmission actually work? It all starts at the back of the engine. The crankshaft turns the flex plate, and bolted to the flex plate is the torque converter. The torque converter takes the place of the clutch you would normally have in a manual transmission, but instead of using a dry clutch disc to connect the engine directly to the transmission, the torque converter uses transmission fluid. Inside the converter, you have an impeller, a turbine, and a stator. The engine spins the converter housing and the impeller with it. As the impeller spins, it throws transmission fluid toward the turbine. That moving fluid hits the turbine and starts spinning it. And because the turbine is connected to the transmission input shaft, the transmission starts receiving power from the engine. This is also why you can put an automatic transmission in drive, hold the brake, and the engine doesn't stall. The engine side of the converter can keep spinning even when the transmission side is barely moving. But when you take off from a stop, the converter does something else. The stator redirects the transmission fluid inside the converter and helps multiply torque. That gives the vehicle more torque during initial acceleration. As the vehicle speeds up, the impeller and turbine begin spinning closer to the same speed. And once you're cruising, most modern transmissions can lock the torque converter. The lock-up clutch creates a much more direct connection between the engine and transmission. That reduces converter slip, lowers heat, and can lower engine RPM. Now that power has entered the transmission needs hydraulic pressure before it can actually control anything. That's where the transmission pump comes in. The pump moves transmission fluid throughout the transmission and creates the hydraulic pressure needed to operate it. That fluid doesn't just lubricate everything, it's also what actually applies the clutches inside the transmission. Without enough fluid pressure, those clutches can't hold properly. And if they can't hold, they slip. When they slip, they create heat, and that's one of the fastest ways to destroy an automatic transmission. Now we get to the gears. Instead of using a bunch of separate gear pairs like you normally see in a manual transmission, most automatics use planetary gear sets. A basic planetary gear set has a sun gear in the center, planet gears around it, a planet carrier holding those gears, and a ring gear around the outside. The crazy part is that the transmission doesn't have to physically swap one gear out for another every time it shifts. The gears are already meshed together. The transmission changes which part of the planetary gear set is being driven, which part is being held, and which part becomes the output. Change that combination, and you change the gear ratio. That's how the same gear set can help create first gear, second gear, direct drive, overdrive, and even reverse. So what actually controls which pieces are allowed to move? Clutch packs. Inside the transmission are stacks of friction discs and steel plates. When hydraulic pressure is sent behind a clutch piston, it squeezes those discs together. That locks certain transmission components together. Release the pressure, and that clutch releases. Different combinations of clutches create different gears. Some transmissions also use bands that wrap around drums and hold certain components stationary. The exact setup depends on the transmission, but the idea is the same. Apply one set of clutches and you get first gear. Release one and apply another and now you're in second. Change the combination again and you're in third. That's also why a transmission can lose one gear while the others still work. If one specific clutch pack burns up, the transmission may lose only the gears that depend on that clutch. So what happens when the transmission actually shifts? Let's say you're accelerating in first gear. Engine RPM comes up and vehicle speed increases. The computer decides it's time for second. The transmission now has to release one clutch and apply another at almost exactly the right time. If the next clutch applies too quickly, the shift can slam extremely hard. If it applies too slowly, the transmission can flare between gears. That means the engine RPM jumps because neither clutch is holding the transmission properly. And every time those clutches slip, you're creating heat and wearing away friction material. Controlling all of this is the valve body. The valve body is basically the hydraulic control center of the transmission. It's filled with passages that route transmission fluid to different areas. On modern transmissions, electronic solenoids inside the valve body control that fluid. The computer watches things like vehicle speed, throttle position, engine load, transmission temperature, and other sensor information. Then it commands the shift solenoids. Those solenoids change where hydraulic pressure is being sent. One clutch releases, another clutch applies. The planetary gear set changes ratios. And the vehicle keeps accelerating. All of this can happen in a fraction of a second. Older automatic transmissions did a lot of this without computers. They used hydraulic pressure, governor pressure, vacuum modulators, throttle valves, cables, and mechanical linkages to decide when to shift. The basic transmission still worked on the same idea: control hydraulic pressure and control the clutches. Reverse works the same way. The transmission applies a different combination of clutches or other holding elements. That changes how the planetary gear set rotates and causes the output shaft to spin in the opposite direction. The engine isn't spinning backward. The transmission is reversing the direction internally. Park is different. When you shift into park, you're not just applying another clutch. A parking pawl physically locks into a toothed wheel connected to the transmission output. That keeps the output shaft from turning. And that's why it's a good idea to use your parking brake on a hill. Otherwise, the weight of the vehicle can sit against that small parking pawl. Now let's talk about the thing keeping all of this alive: transmission fluid. Automatic transmission fluid has several jobs at the same time. It lubricates the transmission. It creates hydraulic pressure. It transfers power through the torque converter. It helps the clutch packs work correctly. And it carries heat away from the internal components. That's why the correct fluid matters. Different transmissions are designed around specific fluid characteristics. And heat is one of the biggest enemies of any automatic transmission. The torque converter creates heat. Clutches create heat when they slip. Towing creates more heat. More horsepower creates more load. And a higher stall torque converter can create additional heat because it allows more slip before coupling strongly. The transmission cooler takes hot fluid from the transmission and helps remove that heat before sending the fluid back. That's why a good transmission cooler becomes even more important when you start modifying a vehicle. Now think about what happens when something starts going wrong. Let's say the transmission gets low on fluid. The pump may start struggling to maintain proper pressure. Now a clutch doesn't apply as hard as it's supposed to. The clutch begins slipping. That slipping creates heat. The heat damages the fluid and the friction material. Now the clutch slips even worse. Eventually, the friction material can burn completely away. That material gets circulated through the transmission and can contaminate the valve body, solenoids, and other components. One small problem can turn into a complete transmission failure. A worn pump can cause low pressure. A bad solenoid can cause incorrect shifts. A damaged torque converter can cause slipping, shuddering, or overheating. A restricted cooler can let temperatures climb. And enough horsepower can simply overpower clutch packs or internal parts that were never designed to handle it. And this is also why stall converters matter so much on modified engines. A higher stall converter allows the engine to reach a higher RPM under load before the converter couples strongly. That can help an engine with a bigger cam get into the RPM range where it actually makes power. It doesn't magically add horsepower. It helps the engine use its power more effectively. But that extra converter slip can also create more heat. So upgraded converters and better transmission cooling often go together. Now let's follow the entire power path one more time. The engine turns the crankshaft. The crankshaft turns the flex plate. The flex plate spins the torque converter. The torque converter transfers power to the transmission input shaft. The transmission pump creates hydraulic pressure. The valve body controls where that pressure goes. The clutch packs lock different components together. Those clutches control the planetary gear sets. The planetary gears create the gear ratio. The output shaft sends power into the drive shaft. The drive shaft sends it to the differential, and the differential sends that torque out to the wheels. An automatic transmission looks insanely complicated when it's completely torn apart. You've got clutch packs, drums, gears, bearings, seals, springs, solenoids, valves, and hundreds of individual parts. But the basic idea really isn't that complicated. The torque converter gets the engine's power into the transmission. The pump creates pressure. The valve body controls that pressure. The clutches control what gets locked together. And the planetary gears create the different gear ratios. Put all of that together, and you've got a transmission that can take hundreds of horsepower and automatically change gears without you ever touching a clutch pedal. And that's how an automatic transmission actually works. If you want the next video to be a full breakdown of exactly how the 4L60E works and why they always seem to lose certain gears, drop it in the comments. Like the video, subscribe, and follow TorqueList Garage for more engine, transmission, and drivetrain breakdowns.